The Q1 question for today concerned an ideal gas. We don't specify a volume, and we'll talk about why we don't bother to do that. The solution comes out a little simpler, and it isn't difficult then to insert the volume or the number of moles. But we're heating the gas, starting at pressure P naught, temperature T naught, and we go to temperature T. And we want to find the new pressure P, assuming that the volume remains constant and assuming throughout that the number of moles remains constant. Now, I don't know why the camera's a little off there. Okay. Now, very simply then, at constant volume, constant N, we know that P over T remains constant, so that P1 is going to equal T over T naught times P naught. In other words, the ratio of the temperatures. We start at low temperature T naught, we raise the temperature to T. T over T naught is greater than 1. We multiply that by P naught, we get pressure P1. The 1 indicating state 1. We start with state 0, we go to state 1. So the change in pressure between state 0 and state 1. What do we get for the change in pressure? Now, you should be, especially if you weren't here in class, you should be taking these questions one at a time and working them out without reference to the solutions here, because it's fairly simple to do this. Doesn't mean you're not going to miss something once in a while, but you should have been one step ahead of me on this one. What's the change in pressure? Okay, so you should have paused and done that. The change in pressure is just going to be P1 minus P naught, which is going to be this minus P naught, and you can verify that that comes out T over T naught minus 1 times P naught. Okay, now the next question is, how high can we raise water with that temperature difference? Okay, well, again, that's something you should work out. You should write that out. It's a fairly simple expression, fairly simple calculation. Okay, well, the change in the rho gy, the change in the gravitational potential energy related term, is going to equal the change in pressure, so that, or if you prefer, delta rho gy, the y will be the height of the column supported by this pressure difference. But we get this relationship we easily solve, and we find that delta y is going to be delta p divided by rho g. And we check, make sure that has the right units. But rho gy has units of pressure. If we divide something that has the units of rho gy by something that has the units of rho g, we get the units of y. So this is valid. We get delta y is this, and then delta p01 is just this expression here. We plug that in, so we get T over T naught minus 1 times P naught over rho g. And then I choose to simplify this. We really have a complex fraction here, and using common denominator, we get T minus T naught over T naught, and the T naught in the denominator can be expressed down here. We get T minus T naught over rho g T naught multiplied by P naught. Now I'll observe that this expression, if you saw it, wouldn't immediately, looking at this expression, this situation wouldn't immediately pop into your head. But once you have this situation, if you have enough working memory and so forth, you can trace back where all this is related to, in a simple way, to the gas laws and the potential energy term. Okay? So you should be able to make sense of this in some way. The better sense you can make, the better off you'll be, of course. Okay. Well, anyhow, that is your delta y. That is your expression for delta y, and that's going to work for any system that goes from a temperature T naught to a temperature T under these conditions, starting with P naught, etc. Okay, well, what's the energy change then? How much energy do we have to put in to accomplish this change in pressure and this ability to raise water to this height? Again, work that out, but we get delta Q01 is, as we know, the number of moles times 5/2 R, 5/2 R being the specific heat at constant volume for a diatomic gas. Remember, we're thinking 5 degrees of freedom, 1/2 R for each degree of freedom, and you hopefully can go back and understand where that comes from. In any case, it's going to be that times the change in temperature, which is T minus T naught. Didn't mention it here, but one reason I did this simplification is we do end up with a T minus T naught here. And there's our change in temperature, which makes it easier to think about the meaning of the term. And the change in temperature is something we definitely want to think about as we think about an actual physical system. Okay, well, anyhow, this is the expression. So that we're asking for the change in, the heat that has to be supplied per mole. Well, here's your number of moles. If we divide this by the number of moles, we get the heat per mole, which is 5/2 R times T minus T naught. Okay? Now, I wasn't sure when I started this that it was a good idea to work this out in quantities per mole, but as it turns out, that worked out kind of nicely. Anyhow, okay, we have the heat added per mole, and we have the delta Y. And of course, once we figure out how much this gas is going to expand as we go from temperature T to temperature TF, we'll figure out how much water we can expel. And we'll be able to multiply that, the weight of that water, by delta Y to get the potential energy change. Okay, so we're going to head that way.